Hi, and welcome back to Red Siege's series on shellcode obfuscation. In this episode, we're going to take a look at using offsets to hide our shellcode. So, what do I mean by that? So, Corey Overstreet and I were talking about this series. How can we hide shellcode? And he was thinking about ways of hiding shellcode, different techniques that he could use. He came up with this idea of calculating offsets. So, what I mean by that is rather than having a shellcode loader that's full of shellcode values, you have a shellcode loader that is full of the difference between the bytes for each position. So, for instance, our shellcode is FC4883E4. Rather than having that, we would have an array that contains the differences, the mathematical difference if we subtract FC from 48 and if we subtract 48 from 83 and so on and so forth and store that. So it turns out this technique has been around a while. It's used in a lot of different ways. However, we couldn't really find evidence of it being used in a shellcode loader. If you know of one, we'd love to hear about it. And Corey has blogged on this, so you can head to redsiege.com/blog and read his blog on this. But if you want more information, go to Wikipedia and look up delta encoding. So let's take a look at some code so you can understand what we're talking about and see how it works. So here is some Python code that will generate this offset array for us. So what we're going to do is we're going to give it an input file. In this case, it's going to be a file with raw shellcode. And then we're going to read in that shellcode, going to calculate the length of our shellcode. Going to create a new list called offset array. We're going to create a new index variable, but we're going to start at 1, not 0, because we want to start at the second byte of shellcode. And that's because we're going to grab the first byte of shellcode, which is in this list called raw sc. We're going to grab the first byte, that's index 0. And we're going to set that value to previous byte. Or rather, we're going to set the value of previous byte to the shellcode byte that's at index 0 in our raw shellcode. Now we're going to loop through all of our shellcodes. So while the index value, which is currently 1 on the first iteration, is less than the length of our shellcode, the current byte value is equal to the raw shellcode remaining index. Now, at this point, remaining index is 1. So we're going to go to position 1 in our raw shellcode list, and we're going to subtract the previous byte. So right now, raw shellcode remaining index is 83, or excuse me, is 48. And the previous byte is FC, because remember our shellcode starts out FC 4883. So in the first iteration, raw shellcode remaining index is 48 minus the previous byte, FC. Now, because we're in Python and not in C, if we were in C using unsigned characters, this wouldn't be a problem. But in Python, we have to deal with the fact that if we subtract a larger value from a smaller value, it'll become negative. And if that happens, then we need to increment that value by 256 to get the positive value instead. And then we're going to append that output into our offset array. We're going to increment, or rather, we're going to then set the previous byte value to the raw shellcode remaining index. So now previous byte is going to be 48. In the next iteration, the current byte will be raw shellcode remaining index, which at this point is going to be 83. We've incremented that one. So FC 4883. So it'll be 83 minus 48. That's what we're going to store here, and so on and so forth. So let's take a look at what the output from that actually looks like. So we've got a variable that we store our first byte. We need to know where we start, and that is going to be FC. And then In this case, this is just some calc shellcode rather than the full interpreter payload that we've been using in the past. And here, so we know that the bytes of that still start with FC4883E4. But you know what? Let's do this. Let's be consistent with the example. So, all right. So we're gonna get our shellcode our regular interpreter bin that we're used to. We've got that value here, and we will paste this in. Oops. All right. And we'll go ahead and save this. So we've got our first byte. We have our delta array, which our shellcode is 598 bytes long. However, deltas is one less. And it's one less because we've already captured our first byte here. So it's the 598 minus our first byte. It's 597. Meanwhile, we're going to declare a new shellcode array of 598. We're going to set the first byte of the shellcode array, index 0, to first byte. We're going to populate that. Now we're going to loop through our remaining deltas. So shellcode IDX equals delta IDX plus 1. So when we first run into this loop, delta IDX will be 0. So shellcode IDX will be 1. And that's because we already wrote the first byte into the shellcode array here. Otherwise, we'd overwrite that. So we have to increment it by 1. And then the shellcode at shellcode IDX is equal to shellcode delta IDX. So shellcode 0 plus delta 0. So now we're going to take FC, which is in shellcode 0, and add 4C. If we add FC and 4C, we get 48. And then if we take 48 and 3B, we'll get 83 and so on and so forth. And that will reconstruct our shellcode. So let's go ahead and compile it now that I've changed it. See if this works. Oops, got a minor error here. So let's take a look at why that is. 39. And that's because I changed the shellcode variable to shellcode instead of E. There we go. Now, when we print out or when we run the program, it prints out the values FC4883, E4. So we can see that here. And if we go down to the bottom of our shellcode, we'll see that that ends in FFD5. So we can see that here ends in A256 FFD5, which is exactly what we expect. Now, how does it fare against Defender? Let's check that out. So we see that it did find a detection here. But when we look at the bytes that are being detected, It doesn't appear that it's detecting shellcode. It looks like it's detecting the routine itself. So now we have to get creative and figure out where we could do that. There's not a lot with this. So there's the logic here. So let's go ahead and compile a new version. We'll run it just to make sure it works. We got the output we expected. And now no threat found. And the reason, of course, that is because they have already, Microsoft has already signatured this. We just wrote this technique here very recently. In fact, in the last few days, and they've already implemented a detection for this. So now we have to have this printf here to break up that signature. Let's see how it looks at virus total. So now it's analyzing. We see that there are some detections for it. So now there are 4 detections. So this ended up being about the same as Jigsaw and Jargon. Now, note that earlier this morning, this technique scored 2. So things are things do change. They're not always consistent with virus total. We could run this again. We might only get 2 detections. So know that when you are dealing with obfuscation and you're testing out your payloads, it's worth testing multiple times against multiple engines to make sure you understand exactly what's happening. So, with that being said, now you understand the offset technique. I want to thank you for joining us today. If you want to read about Corey's blog on the Delta encoding technique, you can go to redsiege.com/blog and look for the Delta encoding technique, and you'll be able to find this code on GitHub as well. That's redsiege, or excuse me, github.com/redsiege. So with that, thank you. I hope you've been enjoying this series. And in our next episode, we'll give you some ideas for future thought and wrap up the series. Thanks for being with us.